Welcome back. Today what we're going to be working on is inclined planes. This is a new journal entry, so please open up your journals and let's get started. So, you've done some of these inclined planes by looking at some of the things in your journal, or in your, yesterday in Giancoli number 40. And so, what I'd like to do is take some time to explain inclined planes in a little bit more detail. So let me just kind of scoot that over here. And let me see if this friend of mine will help me. Yes. We have R2-D2 here. And he's sitting on an inclined plane, or he will be here in a second. So now we're adding another layer of reality to our physics world. And so what we want to see is if R2-D2 is sitting on an inclined plane, perhaps the entrance dock to the Millennium Falcon, I don't know. But if he was just sitting here, what type of forces are acting on him? How can we incorporate friction? Can he slide? All of these things. So, to start off, the first thing that we usually like to talk about is we need to do a free body diagram. And so the free body diagram for R2-D2 is going to be, the first force we need to draw is his, whoops, we don't want to do that. The first force we want to draw is his force due to gravity. And so I'm just going to draw this as a nice big arrow here. We're going to say this is the force due to gravity. And so this is acting straight down. And so you can see we have a little bit of an issue here because right now we've got this plane that's inclined, but the force due to gravity is at an angle to this plane. And so in order to make this, in order to do this so that we can figure this out a little bit better, what we need to do is we're actually going to rotate our axes. And so what we're going to say is everything that's parallel to the plane is going to be our x-axis. Everything that's perpendicular to the plane is going to be our y-axis. And so you can see I'll put a little perpendicular sign there. And so all we're doing is we're rotating our x and y coordinate systems so that the x is parallel to the plane, the y is perpendicular. But what you can see though is that our force due to gravity is not fitting there. But what you're probably saying is, I bet we can use our vectors to turn this, to resolve this vector into two component vectors. And yes, we can. We're going to be drawing a line here, and this is going to be our force of gravity in the y direction, meaning that this is the component of gravity that's perpendicular to our plane. And then we're also going to use another vector here, and this black arrow is going to represent our force due to gravity in the x direction. And this is, let's see if I can adjust this a little bit. Oops. And so what this is going to do, oops. Okay, sorry, I had to do a little redrawing. I hadn't made my triangle quite a right triangle. So what we have here is the black line is representing our force of gravity that's parallel to the plane, and the green arrow is representing our component of gravity that's perpendicular to the plane. So what we've created is a right triangle. The next point is, in order to figure out what these components are to split our gravity up, is we have to know the angle of the plane. And so if we go and say that this plane is at a given angle above the horizontal, it turns out that this angle here is the same angle. And so we could work this out. I could show you using similar triangles. But one of the ways to think about this that I think makes a little bit more sense is if you imagine this plane, if we could pivot this, and so let me bring a pointer in so that you can see what I'm talking about. So, there we go. If you could pivot this plane along at this point, then when the angle here approaches 0, the angle inside here would also approach 0. And so hopefully kind of thinking about that, like if you think of this as a dynamic system, that when the angle of the plane is 0, the force of gravity in the y direction is going to be equal to the force of gravity, because everything will be pointing straight down, and the force of gravity in the x direction will reduce to 0 when this angle approaches 0. And so as we pivot this plane up about this point here, as this angle is increasing, this angle is going to increase at the same rate. So, wow, hopefully that helps. Anyway, I'll get rid of that. So what that leads us, though, is that now we can analyze this using our trigonometry functions. So the force of gravity in the y direction, which is perpendicular to the plane, is merely equal to the hypotenuse, which is our force of gravity, times, and since this is the adjacent side, the cosine of the angle. And our component of gravity that's parallel to the plane is again the hypotenuse, which is the force of gravity, the weight, and since this is opposite the angle, it's the sine of the angle. And so now that we can figure all that out, we can do a little bit more magic, because what we can say is that this force of gravity in the x direction, let's just move it up here, because right now this is just showing you how we made this from a triangle. But let's just move it up so that it just shows that this is the component of gravity that's pulling R2D2 down the plane. And so if that's the component of gravity that's pulling R2D2 down the plane, then our green arrow is representing, yes, maybe you already realize this, but it's representing the amount of gravity that's pulling R2D2 into the plane, which is then being counteracted by the normal force. And so the normal force is going to be equivalent in magnitude to the component of gravity in the y direction. And so F norm equals Fg sub y. And so then we have Fg of x, which is what's pulling R2D2 down the plane. And so then what's left is we would have any possible friction that would be pulling, that would be keeping R2D2 from going down. And you guessed it, the force of friction, you already know the equation. It's the coefficient of either kinetic or static times the normal force. And so now you can figure out all of your forces. Okay, so at this point, hopefully what you can get is, please pause the video for a second, make sure that everyone in the class has the sheet that's titled Practice with Inclined Planes, Forces, and Free Body Diagrams. It has 4 problems on it. What I'd like to do is go over one practice problem so that we can see how this works. So again, please pause the video and make sure everyone has that sheet, and then we will resume and actually look at one of the problems. Okay, so what I'd like to practice here is, let's start with number 1 on that sheet, and in this case we have the mass equaling 5 kilograms, and this object is sitting on a 60-degree incline, and so there's no friction, so we know this is obviously going to start sliding. And so to start off with, we know the weight of this box is its mass times the acceleration of gravity, which means that our force of gravity is 50 newtons. Of course, like we talked about, what we're doing is we are rotating our xy axis so that this is our x-axis parallel to the plane, and this is our y-axis perpendicular to the plane. So what I'm going to do is draw this, which is my force of gravity in the y direction, and I will draw this, which is my force of gravity in the x direction. These two are perpendicular, so they're 90 degrees apart. We've created a right triangle, so this makes it very easy to solve. Force of gravity in the x direction, we said, is our force of gravity times, let's see, I need to go back. Remember we said, there we go, this angle, 60 degrees, has to be equal to this angle up here, also 60 degrees. And so I'll go ahead and label that. This is also 60 degrees. So you can say our force of gravity in the x direction is our 50 newtons times, since we're going opposite that angle, sine of 60 degrees. And this comes out to be 43 newtons. We can do the same thing here with our force of gravity that's perpendicular. This is going to be 50 newtons times the cosine of 60 degrees. And when we work that out, that comes out to be 25 newtons. So we talked about this with our previous example, and we said that we actually know what our normal force is. Not that we need it for this problem, but just for fun. We know that the normal force has to be equal to our force of gravity in the y direction. So the normal force is 25 newtons. And then we also figured out, I'm just going to go ahead and move this force over to here just to make it a little easier to see. We know that this is our force of gravity in the x direction, which was 43 newtons. And so if we're trying to find our acceleration, then the acceleration is equal to F net divided by the mass. And so in this case, since the normal force and the force of gravity in the y direction, let's see. There we go. So right here, our normal force and the force of gravity in the y direction are equal. Then we know that those balance out. So in this case, the only force that's unbalanced is this force of gravity in the x direction. But we could possibly have friction here. In this example, we saw that the force of friction was equal to 0. So this was just already given the problem that the force of friction was 0. But just for fun, let's go ahead and put this in. And so our net force is actually going to be the force of gravity in the x direction minus friction for your future problems divided by the mass. So in this example, it's only going to be 43 newtons minus 0 all over 5 kilograms, and that should result in 8.7 meters per second squared. So there you go. That's how you do that problem. So just to help you out, I wanted to go ahead and give you the answers for problems 2, 3, and 4. so that you can work on those in class and see if you're getting the right answer. So problem number 2, if you do that correctly, the acceleration should come out to be 2.5 meters per second squared. Number 3, again, if this one now has friction involved, so don't forget to subtract the friction. But if you work this one out correctly, it should come out to be 5.6 meters per second squared. And then number 4, this one has some small numbers. Again, it depends a little bit how you do your rounding, but basically within rounding, you should come out with 0 acceleration, because the force of friction should equal the force of gravity in the x direction. There you go. So the last thing that I wanted to look at is whether or not something will move. So in this one, I wanted to see, will an object move? Because if we have something sitting on an inclined plane, the question is whether or not we need to use our static friction or our kinetic friction. And so that's what we're going to look at. Whoa. I also realized I can do 2 pointers at once. Oh, sorry, okay. I digress. Woo, will an object move? Yes. So we get to have a couple of rules when we're doing this. And so when we're trying to find out whether or not an object will move, we have to first figure out if it has reached its maximum static friction. Because remember, the static friction is what's going to hold it in place, and if there's enough applied force, it'll break that static friction and cause it to slide. So the first part is we have to determine if the applied force is greater than the static friction force. So is the applied force, or if you're on an incline, the force of gravity in the x direction greater than the force of friction static. And so what you have to do is you have to compute that. So the force of friction static, the maximum is the coefficient of static friction times your normal force. And so if this is greater than your applied force or the force of gravity in the x direction, then it will not move. And so we can say if, I'm just going to abbreviate this to F static so I don't have to write friction. So if the force of friction static is greater than Fg of x, or some applied force depending on your situation, then what we'll have is no movement. Didn't quite get that either. But if we have the opposite, where the force of friction static is less than the applied force, then that means that the applied force is greater, and so in this situation, if we have this here, then it will move. And so all you have to do in that situation is, if it's moving, so if moving, use F friction kinetic. And so then all the same things apply. When you're trying to find your acceleration, you use the kinetic friction. So that's all that you do. Fairly simple. So your homework tonight is to work on the mu of vectors. Good luck, and I hope everything goes well.